In this video I'm going to take a look at how we deal with the OH and NH protons in NMR spectra. So you can see written up on the board there are three main reasons why these protons cause problems in NMR spectra. So the first one is they have a very wide range of chemical shift values. And if you look at the data sheet, you'll see what I mean there. Another problem they have is they give very broad signals. And the third and final problem is they don't really have any splitting patterns associated with them. So the best thing to do is to get rid of them. And they do that by using a substance called D2O, also known as heavy water. And basically all it is a water molecule where the regular proton, so hydrogen 1 isotope, is removed and replaced with the hydrogen 2 isotope, which is called deuterium. And if you remember back to the first NMR video, any nucleus with an even number of nucleons, remember that's protons and neutrons added together, does not possess this property called spin. And if we think about the hydrogen 2 isotope, we've got one proton, but we've also got one neutron. And so we've got two nucleons, no spin. So the protons in this molecule don't cause any resonance. So basically these three steps are performed. So the first step would be to run the NMR spectrum as normal. The second step would be then to add a small amount of D2O to the sample, and then they would run the spectrum again. And you'll notice in red there, any OH or NH signal will disappear. So I'll explain what happens there now. So if we look at the equation I've drawn up, you can see an ethanol molecule there reacting with D2O. So that's obviously this second step here, and if you look at the equation you can see what's happened. The hydrogen that's bonded to the oxygen, so only the OH proton, is replaced with a deuterium isotope. And so instead of this being present in the sample, when you rerun the spectrum, you've got this here. And you'll notice that we've now got a deuterium which doesn't have any spin, and so the signal due to this group here will disappear. If I'd had an NH, so I could have had an amine or something in here, same sort of thing happens. So the NH protons are replaced with deuterium isotopes, and again their signal disappears in the second spectrum. So if we take a look at the spectrum now for ethanol, I've drawn up the displayed formula here for the ethanol molecule, and I've only drawn the signal due to the orange protons here. So this is the HC single bond O environment. So you can see this orange quartet here, and remember it's coming out as a quartet because it's adjacent to a CH3 group. 3 plus 1 is 4. And the red part of this signal is due to the OH proton. So straight away you can see a problem there, because obviously this is going to be traced out in black by the machine, and you're going to possibly be led to think that this peak here is part of this peak, so it could cause some confusion. And so therefore what you would do is you would add some D2O to the ethanol, and because deuterium doesn't possess spin, the peak disappears. And so all you need to worry about are the hydrogens in the rest of the molecule. So it's a bit like playing now you see it, now you don't. Any signals that disappear are obviously due to protons belonging to an OH group or an NH group. And so if it disappears, it must be one of those. The name given to these protons, so the OH, NH and SH, I haven't mentioned SH, but it's the same with those as well. They're referred to as labile protons, and all that means is they are readily changeable. So I've drawn up an ethanol molecule on the left there and an methylamine molecule on the right. So they contain these labile protons. So there's the labile proton in ethanol, and these are both labile protons in the amine. So what that means is, if there's any tiny trace of solvent present, so there might be a tiny trace of water present, then the protons in the water can rapidly interchange with this proton here, and the same with these here. And the overall effect of that is it makes the signals very, very broad. And the other thing is we don't get the signal from this proton being split by these labile protons either. And so if we think about the CH2 group in ethanol, all we would see would be a quartet due to the adjacent CH3 group. So we don't factor in any OH effect on the splitting pattern. And if we think about the methylamine, yes, we've got two adjacent hydrogens on the NH2 group, but because these are labile protons, they're constantly on and off from traces of water, then this would just be seen as a singlet. And as I mentioned at the very start of the video, the OH protons and the NH protons are always seen as singlets. So hopefully you can appreciate why now, because they're constantly on and off the molecule. So we'll finish this video with a worked example. I've sketched there the Proton NMR spectrum for a mystery substance with molecular formula C3H7NO2. We are told that on adding D2O, the peaks are delta 11 ppm and delta 5 ppm. They are removed. And the other bit of information we're given are the integration values. So we've got integration values of 1, 2, 1 and 3. And obviously the challenge is to work out a possible structure for this compound. So we'll start with the peaks that disappear when the D2O is added. Remember, they will be due to OH or NH protons, which we've got both in this example. So if we look at the shift value of 11 for this one, that corresponds to the carboxylic acid environment for the proton. And you can also see that we've got an integration value of 1, which sort of goes with the fact that there's one hydrogen in this environment. So the peak at delta 11 is COOH. The peak at sort of 5, this one here, another singlet. Remember, these OH and NH signals always occur as singlets. This time we've got an integration value of 2, so there are 2 protons in this environment relative to this one, and that would be consistent with an NH2 group. The NH environment does resonate at around about the 5 ppm mark, so we could safely say that this must be an NH2 group. If we look at the peak to the far right now, sort of roughly delta 1 ppm, we've got a doublet here. So that means that the protons in this environment, the protons giving this signal, must be adjacent to one non-equivalent proton. So there's a CH adjacent to these protons. And the number of protons in this environment must be 3, because we've got an integration value of 3. So it looks like we've got a CH3 group adjacent to a CH group. And then if we look at this signal here, that kind of confirms what we've just said. In this environment, we've got one proton, and it must be adjacent to a CH3 group because we're seeing this one proton as a quartet. So remember, adjacent is 3, so the signal comes out as 4. And if we put all the bits together, it looks like we've got this amino acid, which obviously fits in with this molecular formula here, C3H7NO2.